So, so let me just say one more brief word about canonical forms, because we'll be using it over and over again. I said it towards the end. I want to say something about triangulation and canonical forms. So let's go back to this example of the quadrilateral that we talked about. So one way, so we saw that the canonical form for a triangle was really easy to get, right? And especially if we write y as z1 plus alpha 2 z2 plus alpha 3 z3, then this canonical form was just d log alpha 2, or d alpha 2 over alpha 2, d alpha 3 over alpha 3. Okay? Now, actually, let me just even at this level, and of course, more invariantly, it was this y d squared y 1, 2, 3 squared over y1, 2 to y3, 1. But I want to say something a tiny bit more about this form. So probably Jake and Alex perhaps talked about this notion of positive coordinates associated with the Grassmannian or fancier things. And so I want to say something about that here. So the important thing about these variables is that when we're inside the triangle, they range from 0 to infinity, right? Alpha 2 ranges from 0 to infinity. Alpha 3 ranges from 0 to infinity. I want to say a little bit about how to write this in a slightly more invariant way. Okay? So there's a couple of ways we can write this in a slightly more invariant way. Let me imagine I put the alpha 1 back there for a second. Okay? So now, so if I put the alpha 1 back there, what's the problem with this? There's no problem with it. It's just that everything should be invariant under rescaling all the variables by an overall constant. Okay? So I should be able to just rescale alpha 1, 2, 3 by a constant. So that's like a GL1 symmetry that I've kind of gauge fixed when I write the form in this way. So there's another way of writing the form. There's another way of writing this form, which would be, and so let me write it in kind of a, I could write it like this, but I could say modulo GL1. Okay? And so modulo GL1 here means the usual way we think about gauge fixing. In this case, it would mean, for example, you set alpha 1 to 1, and you also forget about this factor, right? Then it turns into d alpha 2 over alpha 2, d alpha 3 over alpha 3. Okay? So this is the sloppy physicist way of writing this down. There's actually a nicer way of writing it. The nicer way of writing it is I can write like this. Imagine I group all of these alphas into a big vector like alpha 1, alpha 2, alpha 3. Then another way of writing this omega is that omega is alpha d alpha d alpha over alpha 1, alpha 2, alpha 3. Okay? So in other words, this is, so what do I mean by this? This would be, this would be like alpha 1, d alpha 2, d alpha 3 minus d alpha 1, alpha 2, alpha 3 plus d alpha 1, d alpha 2, alpha 3 over alpha 1, alpha 2, alpha 3. Okay? Which is just kind of three of these things, right? It's like this is like d alpha 2 over alpha 2, d alpha 3 over alpha 3 minus one of the other ones plus one of the other ones, right? This is a more invariant way of saying it because now any way of actually putting coordinates on alpha space, right? For example, I could say my coordinates are alpha 1 is 1 and I have alpha 2 and alpha 3, and that collapses to that term. Okay? And similarly for any of the rest of them. Of course, you'll recognize this is exactly like we wrote the general form on any projective space. In this case, the projective space is in the space of the alphas themselves. All right? So these are many ways of writing it. Typically, the physicist's sloppy way is the best, okay? Because in that way, it's clear what you're doing, right? Now it just looks like you have all the coordinates, the d log of all the coordinates, all the positive coordinates, but there's an overall GL1 that you have to fix when you think about the form. But concretely, the fixing always involves choosing this this slightly cool form on projective space that we talked about. Okay, is that clear? Okay, so when you find positive coordinates that cover your space, immediately going along with that is a form. Just the d log of the positive coordinates, perhaps modulo some GL action when it's obviously there. Okay, is that clear? So there are certain simple spaces like this one where there's an obvious set of positive coordinates that just cover the inside in a nice obvious way. Okay, and when you find them, you know the canonical form. I can just write down. I can write this down, and I can go back to this invariant expression easily. Okay. All right. Now, what's the problem with the square? The problem with the square is that there's not an obvious way of covering the inside of the square, right? I can't start in this corner and say that it's z1 plus alpha z2 plus 4 because I have to reach 3 somehow. Okay? So you can try to see whether there's some sort of fancier way that you could foliate the inside of the square in a cool way to cover the inside with one set of positive coordinates. But you can pretty quickly convince yourself for general polygons that you can't do that with any kind of simple linear map of the kind that we've been talking about. Okay? There's a whole separate story that in some cases tells you how to do that, but we won't talk about that here. Okay? So, but when you have positive coordinates, you're in great shape because you immediately know the canonical form. Okay. So what can we do instead here? If we don't want to do all that detailed geometry that we did before in the last before lunch, there's another obvious thing that you could do, or at least another obvious thought, is that the canonical form here could be thought of as the sum. I could triangulate this guy, and the canonical form is, you would intuitively think it's the sum of this one and the canonical form for this triangle and that triangle. So that omega for 1, 2, 3, 4 would equal omega of, for example, 1, 2, 4 plus omega of 2, 3, 4. Okay? Now, why is this reasonable? It's because omega of 1, 2, 4 is putting logarithmic singularities here, right? So that's good. It has singularities there and there. That's good. It has these crappy singularities there. That's bad. That's not a form that we have in this space. But now this guy has singularities here, right? And so on here is the only place there are problems. But it's plausible that singularity should cancel between the two of them. Why is it plausible? Precisely because the whole point is that, let's say from this side, let's say you hop on that edge, right? The whole point is that the residue of what you get there loses memory of where it came from, right? The residue on this edge doesn't know about the rest of the triangle. It just knows about 2 and 4. So the residue of the form on that pole is just the canonical form of this interval 2, 4, which is the same as what it is on the other side. And therefore, if you're lucky about the signs, they can cancel. Okay? So I want to be clear. You see how it's very important that what you had was a canonical form here, right? Precisely because it's a canonical form, and it has the property that the residue on a face is just given by the form on the face, then all the details of what it looks like elsewhere are gone by the time you go there. And so when you triangulate, it's possible for the different pieces to add up and cancel. Okay? It's not completely as trivial as I'm making it sound. So anyway, it's true in this case. They cancel between the two of them, and so we get the right answer. Okay. At the same time, we get a cool identity between rational functions because I can triangulate it this way too, and I get the same answer. So there's an interesting 4-term identity. You know, 1 plus 2 equals 3, 3 plus 4 for the two different kinds of triangulation. Let me just mention why it's not 100% as trivial as it seems. Imagine I had something where I triangulated in some sort of complicated way, like this. Okay, they're not even triangles here, but anyway, let's look at something like this. You see, you might be tempted to say that the pole here is canceling between this guy and that guy, right? But it's not true, because on here, also this triangle up there has a pole there. They all have a pole there, right? They all have a pole everywhere along the line. So it's not quite as trivial as them canceling pairwise along where they meet. However, it still works precisely for the same reason. It works because the canonical form of this guy is that interval. Of the next guy would be this guy would be this one going the other way. That one would be that guy going the other way. This one up here would be this one going that way. And then it's the fact that the sum of all those intervals adds up to nothing on the edge that guarantees, again, recursively, that the residues all cancel. So it's not quite as trivial as things canceling, geometrically, but the fact that it's a canonical form does guarantee that you can get it from triangulation. Okay, so that's the prime method that we've been using to calculate canonical forms. So to do it, you have to solve a geometry problem. You have to figure out how to decompose your positive geometry, just a polygon or a polytope and things that we'll talk about, into pieces that look like something simple enough whose canonical form you know, triangles or simplices, and then you just add up the canonical forms for the pieces. Okay. All right, so that's all I wanted to say about that. And now I want to transition to talking about the amplitude as a particular example of a sort of a large class of positive geometries. And I will talk about it first in the more standard way that's most closely connected to the positive Grassmannian and other things that you've heard about, and then in the slightly newer way where it's formulated purely in momentum twistor space with no direct reference in its definition to Grassmannians of any sort. Of course, they're all sitting there, but it's not part of the. It's not central to the description to begin with. Okay, so. So let me, before doing this, let me take a little a teaser and a kind of a prelude, just so you have some idea of where things are, of the kind of objects we're going to be seeing and dealing with. So let me go back to the formula for the NMHV tree amplitude. And I want to interpret this in a variety of ways. So my goal, given that I'm not going to be able to do everything before dinner, is to at least work through a few examples in detail enough so that we can get to the two examples that I promised to tell you about. But I want to show you in some simple setting ahead of time the kind of the different ways we're going to think about the scattering amplitude as differential forms in what spaces and so on, already at the level of the formulas with this familiar case before we start talking about the geometry. So this is just a little detour in going back to NMHV tree. So there's this formula, the sum of I less than j, 1, I plus 1, j plus 1. And so question number 1 is, what the heck is this 1i plus 1 jj plus 1 structure? What is this, what the hell would make you think about 1i plus 1 jj plus 1 to begin with? And question number 2 is actually to look at the sort of R invariant itself. Okay, so this, so how should we think about this interesting object 1, 2, 3, 4, 5 equals this fermionic delta function 1, 2, 3, 4, eta 5 plus cyclic over 1, 2, 3, 4, 2, 3, 4, 5, 5, 1, 2, 3. And already with this object, I can illustrate a few, really the kind of the three interconnected themes: positive Grassmannian, old amplituhedron, new amplituhedron. Okay? And those three things can already be seen as different interpretations of this formula. Okay? So, the positive Grassmannian interpretation of this formula is the following. And here we're not seeing fancy Grassmannians, but this is the simplest version, is to interpret 1, 2, 3, 4, 5 and as the following object. Did you talk about this, Jake?
I defined it.
You defined the object, but did you write this integral?
In principle, I did. I did it all through. But I didn't talk about positivity or not.
You're not filling me with joy. So, okay.
Why focus on N and HB?
Yeah, I know. You're too cool for school. Yeah. So, all right. So, all right. So let's talk about this formula. Okay. So this is representing this object that depends on momentum twister data. Remember, these are super momentum twisters, but it's representing it as an integral over an auxiliary space. This is mod GL1. So the same way that we talked about before. In practice, it means I can set one of the c's to 1 and just do the remaining four integrals. Okay? But here, there's 4 bosonic delta functions and 4 fermionic delta functions for the fermionic components of Z. How many of you are familiar with this formula? Okay. All right. Good. So we can. So let me. Let's actually explain it. So now you will see how something works. Okay. So, but just to give you the sort of basic structure, what's interesting about it is that we're integrating over this auxiliary space. Okay, so the measure on the space is just the d log of all these variables. Okay, and then all the dependence on the external data is in this kind of simple factor, right? This linear factor, delta 4/4 c dot z. So let's do the calculation. This is, despite appearance, is a very simple calculation. There are 4 integrals here, right? Because there's 4 c's after I gauge fix. There are 4 delta functions. So this is not an integral, right? I can just solve for the c's. All of these formulas that we've seen in amplitudes are just secretly Jacobians. They're just fancy ways of writing Jacobians to make them look cooler, okay? And also expose other structure, not just make them look cooler. But this is just a glorified Jacobian. Is that clear, right? Because I'm just solving for the c's. So let's actually do it. Let's say set C5 to 1. So I'm solving C1 Z1 plus I plus C4 Z4I plus Z5 equals 0. Okay, so I can solve for all the c's. So first, let's solve for all of them, right? Well, we did this before, right? So put a minus sign there. C1 is equal to, what is it? 2, 3, 4, 5 over, no, shit. Over 1, 2, 3, 4, yes. Thank you. And so on. So negative C2 is 3, 4, 5, 1 over 1, 2, 3, 4. And so on, okay? 4, 5, 1, 2 over 1, 2, 3, 4. And negative C4 is 5, 1, 2, 3 over 1, 2, 3, 4. Okay? You remember how we did that at the end of the last lecture, right? So, okay, so let's just shove it in. So this integral is equal to, well, there's a product of 1 over C1 through C4. So we're going to have 1 over 2, 3, 4, 5 over 5, 1, 2, 3. Let me not worry about the minus signs. There's 4 of them, so they'll cancel. And then I'll have 3, 4, 5, 1. Oh, what am I doing? So over 1, 2, 3, 4. Over 1, 2, 3, 4. 4, 5, 1, 2. Over 1, 2, 3, 4. And then 5, 1, 2, 3 over 1, 2, 3, 4. Okay, so that's the 4 c's downstairs, right? Now, But there's a Jacobian from using the delta function. What do you think the, well, we can be rigorous about it, because what is that? That delta function is like delta 4 of this matrix, Z1, Z2, Z3, Z4 as a 4 by 4 matrix dot C1, C2, C3, C4 minus or plus Z5, right? Therefore, the Jacobian is just 1 over the determinant of that matrix of Z's, okay, which is just 1 over 1, 2, 3, 4. That's the Jacobian from the delta function, okay? I should have put the C's on the other side as the transpose, but anyway. And finally, I'm left with the Grassmann part here, which is the delta 4 of, well, C1, Z1 plus so on. So this is just exactly the 2, 3, 4, 5 over 1, 2, 3, 4, A to 1 plus dot dot. And then finally, C5, Z5 is just A to 5. Okay, so I'm doing it once in this brutal, direct way, just so we see that we can do it. Okay, so what happens very nicely? This delta 4, if I pull out an overall 1, 2, 3, 4, there's a 1 over 1, 2, 3, 4 to the 4th. That cancels all of those 4 guys. And what am I left with? This is exactly equal to, it's exactly equal to what it's supposed to be. 1 over 1, 2, 3, 4 up to 5, 1, 2, 3. Delta 4, 1, 2, 3, 4, A to 5 plus cyclic. Okay? Okay? So that's the R invariant written as a Grassmannian integral. Okay? So if I write this one more time, I have something that looks like 1, 2, 3, 4, 5 is equal to an integral dc1 over c1, dc5 over c5, modulo gl1. And then I have delta force. I'm just writing it again, c1 z1 plus c5 z5. But the point is that I can think of this as a form on the positive Grassmannian G15. In this case, this is just 1 by 5 matrix, so it's not much of a Grassmannian, but the coordinates are positive. They go from 0 to infinity, and that's the form with logarithmic singularities on the Grassmannian. So I'm integrating over the Grassmannian of something that looks like C dot Z. Right? So, okay? And in fact, we could generalize this for any old this is for any R invariant. Any old R invariant, A, B, C, D, E, if I have n particles, this is also of this form. So the form dc1 over c1 up to dcn over cn, mod gl1. Let me be now specific about this. And still a delta 4/4 c dot z. So in other words, we can think of this as an integral over the positive Grassmannian G1n. But now I have to be even more careful about the contour that I'm talking about. Okay? So what I need to do when I do this integral is I have to imagine, if I want to say it as an integral, I have to imagine setting all but 5 of the c's to 0. I can imagine doing that on a contour, right? I take a little residue around the logarithmic singularity where the c is 0. So I have to pick a particular contour, a particular cell of the positive Grassmannian G1n. Okay? Remember, positive G1n again is just trivially n positive numbers, and so I could set any of them to 0 that I like to go to the boundaries in this case. So I talk about those cells. There's some particular cell associated with just keeping A, B, C, D, E. And so if I do that, I set everything, all the c's that are not equal to A, B, C, D to 0, and then I'm left with the previous integral. Okay? Is that clear? So that's the Grassmannian way of thinking about BCFW recursion relations and other things. The recursive way of the Anschauer diagram way of determining scattering amplitudes. it has the idea that there's this beautiful universal form on the positive Grassmannian. In this case, we haven't written down the non-trivial one. We've just written down the trivial one on G1n. But there is this form on the positive Grassmannian. There is this simple way that the external data interacts with the form. But the different pieces in the amplitude correspond to different cells of the positive Grassmannian. Okay? You have to take different cells. So for example, I have to take the cells 1, I plus 1, jj plus 1, where all the other c's are 0. Okay? I have to sum over the answer I get from each one of those cells to get the final answer. Okay? So from this point of view, the first thing that has been accomplished is the recognition that the building blocks are naturally tied to the Grassmannian, and via what you heard from Jake and Alex, it's beautifully coupled to the story of on-shell diagrams and recursion relations, and all this stuff has a surprising and beautiful connection to the cell structure of the positive Grassmannian. So we draw these pictures of on-shell processes, and when you really carefully glue the 3 particle amplitudes together to see what you get, it's really associated with exactly these kinds of integrals in the Grassmannian. So from this point of view, we understand what the functions are. The functions are tied to cells of the positive Grassmannian in this way. And now what is left is the question, why do we take these cells and not other cells, right? Why am I adding up 1i plus 1 jj plus 1, right? Why not something else? Okay, so is that clear? Of course, one answer is because that's what you get from recursion relations. That's a perfectly good answer as far as just getting the right answer is concerned. But as far as the sort of conceptual, the search for some different ab initio starting point to define the amplitudes is not satisfactory, because you're still using locality and unitarity to tell you what combination of these objects to take. Let me say it another way. What would be wrong? I mean, let's say I took 1, 2, 3, 4 plus 2, 3, 4, 5 plus 2, 4, 5, 6, and I added them all. It's even cyclically invariant, looks beautiful. What's wrong with it? It's not local and unitary. Okay? It would have all kinds of crazy spurious poles. It would not correspond to something physical. It would be perfectly great as far as the Grassmannian was concerned, alone. The building blocks are perfectly fine, but there's no obvious reason why we're putting these building blocks together in a particular way. Okay? So far so good? Okay, so and this is really the so now let's move on. So now let's move on to give a second interpretation to the same object. Okay? Second interpretation of this formula. Okay, so to do that, we're going to just go back to the. So let me write it like this. Okay. Well, actually, maybe I'll. This way of writing it will make it look like it comes out of the blue very slightly more, but it's actually not as bad as it seems. And just for the sake of time, let me write it this way. Okay, so in the second way of writing this R invariant, we're actually going to get rid of the Grassmann variables. Okay, so what we're going to do is, instead of having z and eta, okay, so instead of having the super object, we're going to do something else. We're going to build a new z. Maybe I'll write it like that. And this guy is going to have 5 components. It's not going to be a 4 vector. It's going to be a 5 vector. The top components are just going to be the normal bosonic momentum twisters. But the last component is going to be different. Oh, sorry. Maybe before sorry. Let me make it look less mysterious before doing that, actually. So let me remind you of the formula we had for the canonical form. So let's go back now to canonical forms for a second, and let's remind the canonical form for, let's say, a triangle, right? The canonical form for a triangle looked like 1 over y1, 2, y2, 3, y3, 1, 1, 2, 3 squared. And then there was this y d squared y part, right? So let's just have fun. What is the canonical form for a tetrahedron? One more variable. Well, a tetrahedron now has 4 faces, right? So for a tetrahedron, we'd have 1 over y1, 2, 3, y2, 3, 4, y3, 4, y3, 4, 1, y4, 1, 2. And then upstairs, we just have 1, 2, 3, 4 cubed. And now y d cubed y. And what about the canonical form for a 4 simplex, whatever it's called? Okay, it would be 1, 2, 3, 4, 5 to the 4th over 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 1, 4, 5, 1, 2, 5 poles, 5, 1, 2, 3. And then there would be some y d4y. Okay? Is that clear? Just keep going. We have more and more faces. Okay. All right. So this is a formula for the canonical form for a 4 simplex, whatever it's called. What is it called? I don't know what it's called. Right? For a simplex in P4. Okay. See, simplex in P4 has 5 vertices, 5 faces, 5 poles, something to the 4th upstairs. Now let's write down the formula for the R invariant again, which is a to 5, 1, 2, 3, 4, plus cyclic to the 4th. The Grassmann delta 4 is just the 4th power divided by 1, 2, 3, 4, 2, 3, 4, 5, up to 5, 1, 2, 3. So this is the canonical form for a simplex, and this is the R invariant. Okay. And if you're Andrew Hodges, you recognize that these things are essentially identical. Right? 5 poles, something to the 4th. Same 5 poles, something to the 4th. Is the similarity clear, I hope? Right?
No y's in the delta.
Sorry? There's no y's, that's true. So that's right. Oh, I'm sorry. There's y's here. I'm sorry. Thank you. And I apologize for my terrible writing. Okay?
In one form, you have less variables.
Yes, exactly. So, okay, so how do we make them precisely the same? Well, if we go back to this guy, if we go back to the canonical form, whatever y is. Now I'm going to focus on this function, right? I'm going to focus on this function of y. So I'm going to talk about this function. Let me write that function down again. So it's 1, 2, 3, 4, 5 to the 4th over y 1, 2, 3, 4 up to y 5, 1, 2, 3. Okay, I have this function. But whatever y is, wherever it is, I can, by a GL transformation, I can bring y to the form, 0, 0, 0, 1. Right? So I can always bring y using a GL5 transformation. These are 5-dimensional vectors now, so I can always bring them to the form 0, 0, 0, 0, 1. And then in that form, each one of the z's, 5-dimensional z's, is going to look like some 4-dimensional z up there. And down in the last component, it has some component. Let me call it xi. OK? By the way, what is the geometric interpretation of this z upstairs? It's very simple. I have some configuration of vectors in 5 dimensions. I also have y, which is some vector in 5 dimensions. And all I'm doing is projecting the picture through y. Right? So literally, you imagine, you'll look in the direction of the vector y, so it gets squashed down to the origin. And then the whole rest of the picture becomes one lower dimensional. Right? So that's exactly what this configuration of z's looks like. It's the projection of the underlying 5-dimensional data through y. All right? But that's the geometric way of saying it. Practically, it means you just do that. When you do any transformation, you bring that the form, and you take the top 4 components. All right. So now let's look at what this function is. What is this function? First, what is the denominator? The denominator is super easy, right? Because you have this y is here. That means that all I get from this big 5-dimensional determinant is just the 4-dimensional determinants made out of the z's. Okay? So this part is easy. I just get 1, 2, 3, 4. These are 5-dimensional things. These are 4-dimensional things. So 1, 2, 3, 4, 2, 3, 4, 5, all the way up to 5, 1, 2, 3. Okay? So the denominator is looking really good. Now the denominator is exactly the denominator of the R invariant. Okay? And now what about the numerator? Well, the numerator is also really easy. It doesn't have any y's in it, right? But what is it? If I just take this big determinant, for example, this determinant is xi5 times 1, 2, 3, 4 plus cyclic, just expanding the determinant in terms of the bottom row. Okay? And it's that whole thing to the 4th. Okay, so now it's looking really close, right? Looking really, really close. There's still a difference, though, that this xi, this is a bosonic object, and there are some Grassmann crapola here, right? So now comes the final weird step. And it was a weird step all along, but it's perfectly well defined, is you just declare that xi is infinitesimal. So xi, it's a bosonic variable, but it's infinitesimal in the sense that its 5th power is equal to 0. Okay? Here, I'm allowed to do that. Another way of saying it is I'm doing a Taylor expansion in this guy and only keeping the terms of 4th order in x's. Perfectly allowed to do that. But if I want to say it formally, then I say the xi for each particle is actually some Grassmann variable phi times another Grassmann variable eta for each particle. And a runs from 1 to 4. Okay. If this is weird, it's weird. Okay, it's not much better than this in real life. This is real life. Okay, so you write xi as phi dot eta in this way. So now this expression is still bosonic. It's some phi eta 5 plus cyclic, right? But then I do the only thing I can to get rid of this Grassmann variable, these Grassmann variables. Phi, I integrate over them. Grassmann integrate over them. So if I d4 phi a of now this 1, 2, 3, 4, 5 to the 4th over y 1, 2, 3, 4 up to y 5, 1, 2, 3, that is the R invariant. Okay? So this seems a little bit out of the way. It's kind of a slightly funny dictionary, but I have a simplex now. I have a simplex in P4, and the canonical form for the simplex, if I strip off this universal y d4y part, the function that goes along with the canonical form is essentially the R invariant itself. But you have to interpret it by thinking about y, by thinking about z as being a 5 vector, not a 4 vector. The Grassmann information is buried in the extra components of z. And there is this other object, y, sitting around that tells you what part is the bosonic component and what part of the Grassmann components. Okay? And so this dictionary lets you go from this purely geometric object, which is the canonical form for something, okay, to the actual scattering amplitude. Okay? So this is the second interpretation now. It's a second interpretation of the R invariant. This one does not manifestly look like a Grassmannian integral. I didn't present it that way. What you can show very easily is that there's this way of converting etas to bosonic things can be done for all the cells of the positive Grassmannian. It's just another way of writing that delta 4/4 formula. Okay? Another interpretation, this bosonic interpretation of this delta 4/4 formula now associates with every cell in the positive Grassmannian this purely bosonic object that you can interpret as a form that lives in this Y space. Okay?
So
Yes?
you have some ambiguity in this construction. So here I understand that you really can keep ambiguity that can correct out.
No, here there isn't any. Here, I mean, the way I just wrote down the answer and I was trying to motivate it. But you can really go to the Grassmannian formula and rewrite it by introducing. Essentially, you can take the delta 4 for the eta part and write the delta 4 for the eta as an integral over d phi of something, and then just undo the procedure to discover the y's in this way. Okay. So
General question.
yes.
If you do not have any Grassmannian, you have amplitude then I'm not sure that there is a well-defined precision going down.
There's a well-defined what?
There is I'm not sure that there is a well-defined precision to point down this way.
Well, so I mean, I think we haven't talked about the amplitude. Let me come back to your question in 10 minutes, okay? So this is still motivational, but I'm giving now a second formula, okay? The second formula is that the amplitude. So now let's decide. Since we know how easy it is to go back and forth from this purely bosonic thing with y's to the superamplitude, we're just going to talk about the thing with the y's for this part of the discussion. Okay. So now I have this object 1, 2, 3, 4, 5, by which I really mean y d4y 1, 2, 3, 4, 5 to the fourth over y 1, 2, 3, 4 up to y 5, 1, 2, 3. And so now I'm going to talk about a form which is exactly the same formula, the sum over I less than j of 1 I plus 1 j plus 1. Okay? And now each one of these things is interpreted as the canonical form for some simplex in this abstract P4. Not P3. The momentum twistor space is P3. Now this geometry lives in this higher dimensional space P4, where I've made room for the extra supercomponents, right? Okay? Okay, so this is way 2. This is the second picture for amplitudes. Already here we've encountered a novelty that we should be thinking about the amplitudes as a form. Okay? But it's a form on Y space, right? So the form in this funny abstract Y space. I can tell you this was an important conceptual step in thinking about the amplituhedron because I just started off telling you about Y as just some dummy thing that was fixed to 0, 0, 0, 1 and so on. It's sort of now very important to think about the action being in Y. You even think about this external data as sort of fixed and sitting there. And this form, we care about how it depends on Y, the fact that it has logarithmic singularities on all these boundaries and so on. Okay, so now the action is in this Y space. And this Y space already here is P4. It's not P3. Okay, so it has nothing to do with the space of the original momentum twistor data. In general, for general K, so this was K equals 1, where Y is a one plane in 1 plus 4 dimensions. Said another way, there's just some y capital I, and I runs from 1 to 5, or 1 plus 4. And the z's also are I equals 1 to 1 plus 4. For general k, we have ky's, and k is actually, y is a k-plane in k plus 4 dimensions. And the k plus 4 is that the z's themselves are k plus 4 dimensional vectors. It's 1 to 1 plus k plus 4. Okay? And so we've made all this extra room in k extra components to get the Grassmann weight. Okay? So now we wouldn't just have one phi, we'd have k phi's. The extra components would be phi dot eta for all the extra pieces, and we'd integrate over all of them. But still, we're interested in a canonical form that lives on this funny space, this Grassmannian space of k-planes in k plus 4 dimensions. Okay? Now, what we've seen, what we saw before, and this is pure transcription. Okay? At this level, apart from the significant inspiration to add these extra components and go to this other space, still, everything is still naturally connected to the, it could be naturally connected to the Grassmannian on-shell diagram picture. Beforehand, with a cell from the Grassmannian, we got a function of z and eta. Now from the same old cell in the Grassmannian, we get a canonical form, so some kind of form on the y-space Grassmannian. Okay? And we still have to add them up in just the way we did before, except that now the resulting object that we're going to get is some form that lives on this space of k-planes in k plus 4 dimensions. Okay? So that's the space in which the amplituhedron lives. Okay? At least at tree level, it's the space of k-planes in k plus 4 dimensions. All right, so now we solve the same question that we had before, but it already has a slightly different character to it. Because now each one of these pieces is more vividly associated with some geometry, right? So each piece there really looks like it's the form that goes along with the simplex, right? So you can hope that these things are gluing together to some natural, nice geometric object. So let me give you a easier to visualize toy example. So a toy example is as if, to begin with, our momentum twisters were just 2-dimensional and not 4-dimensional. Okay? So I'll just chop everything down in, by dimension in 2. And this is of relevance for various limits of scattering amplitudes and so on. But anyway, so let me do a toy R invariant, which is just 1, 2, 3, which would be, if I write it in Grassmannian form, dc1 over c1, dc2 over c2, dc3 over c3, mod gl1. And now instead of delta 4/4, I'll put delta 2/2, c1 z1 plus c3 z3. Okay? And in formulas, it would just be eta 3, 1, 2 plus cyclic squared divided by 1, 2, 2, 3, 3, 1. Okay, so this is a toy R invariant. Is it clear? It's a smaller version of the thing that we had before. So this would be the Grassmannian form. What would be the What would be the amplituhedron form? Just the transcription is I would have 1, 2, 3 equals y d squared y, 1, 2, 3 squared, just a canonical form for a triangle, y 1, 2, y 2, 3, y 3, 1. And now, what is the analog of the amplitude, or the form? The form would be the toy analog, instead of a sum over I and j of 1 I plus 1 jj plus 1, let's just lop off two indices, right? We're just throwing out two indices. So this is just going to be the sum over I, 1 I plus 1. Okay? So just pretend the world had two fewer momentum twistor variables, and we were Grassmannian people, on-shell diagram people. All the same stuff would go through. We would discover formulas that look like the sum of R invariants like 1I plus 1. We would discover the connection to the Grassmannian. We would discover that we could bosonize and write in this Y space. And so we'd be left with this thing and the question, why do I add 1I plus 1? What is this about? What are these 1I plus 1s? All the same words I could say about this. And here you would know what to say, right? Because what is this? This is 1, 2, 3 plus 1, 3, 4 plus 1, 4, 5 plus what done. And so what is this? This is just the triangulation of a polygon. Okay? 1, 2, 3, 1, 3, 4, 1, 4, 5, and so on, right? And isn't that beautiful? Right? So you have this collection of objects. You don't know why you're adding them up together. That was the question, right? Each one of them is associated with the cell of the Grassmannian. Everything is great. But the question is, why? What are they doing? Why would I ever think about these 1I plus 1s? Why am I putting them together? And the answer is that there's another thing out there that's more intrinsically what the thing is. It's the canonical form of the polygon, right? And so that is the question. So you're given the polygon, and you want to know what is the canonical form of the polygon. And you can represent it in many different ways. And we can triangulate it many different ways. And they'll all give us different formulas that are related by, they're all related, by the way, by the simple identity that a square can be triangulated in two ways. That's the basic identity. All the rest of them are just linear combinations of that one. Okay? So in this toy example, we found what is the intrinsic object. The intrinsic object is the inside of the polygon. And so we've seen our first toy example of how there's some intrinsically God-given geometric object, the polygon, whose canonical form calculates the toy amplitude. Okay? Any questions about this? All right. So now let's go back to the real problem. And actually, we should not have been so happy even here. We're happy because we've seen polygons before. So another general fact of life in this business is it's absolutely crucial to draw pictures and have geometric pictures of what's going on. But by the time you really fully understand something, or on the way to fully understanding something, it's really important to challenge yourself to explain it to someone who you imagine is blind. Okay? Imagine you couldn't look at a blackboard, you couldn't visualize. This is very important because we're not far from this ourselves, right? I mean, we can visualize two-dimensional things, but I can't begin to visualize what four-dimensional polytopes looks like, okay? So anything you're going to do is going to have to have a more basically algebraic flavor to it by the time you're done. A, because we can't visualize, and B, because it ultimately something sort of algebraic and kind of more combinatorial always ends up being more fundamental, at least in my experience, than the geometric pictures. So let's go back even before moving on to the four-dimensional case that we care about, and let's talk about this polygon a little bit more invariantly already. Okay, so now we're going to spend some time talking about the inside of a polygon. So let's say I want to talk about all the points on the inside of a convex polygon like this. And well, so we know that all the points on the inside look like yi equals c1 z1 plus cn zn. where all the c's are positive, right? That's what we said before lunch. Now, I emphasize this is a very redundant description of the inside of a polygon. The polygon is two-dimensional. I have n variables here, or n minus 1 variables projectively. So it's very many to one map. This is kind of a useless formula. If someone hands you some y and says, is this y inside the polygon? This is a very hard formula to use, okay? Because you can write the y as a linear combination of a bunch of z's, if you like, but it could have plus and minus signs in it. This just says there must be some way of writing it in terms of a sum of z's with positive coefficients, but it doesn't tell you how to do it, okay? And it doesn't tell you how to check. Notice that when I triangulate, let's say, I can triangulate by saying that it's in like that, then each one of the insides of these triangles, the inside of one of these triangles is what I would get if I set all the c's other than 1, 2, and 4 to 0, right? So if I set all the c's other than 1, 2, and 4 to 0, then I'm on the inside of that triangle. That's just what we said a moment ago, right? The inside of that triangle. So in other words, all the y's here are, I imagine fixing the z's, and I scan through all positive c's. So here, I can write this as, loosely c dot z, where the c is in the positive G1n, right? But when I triangulate, I have to go to low-dimensional cells, two-dimensional cells of positive G1n, where I set all the variables but 3 to 0, right? And as we just discussed, there's many collections of those two-dimensional cells that I can use that tile the space. No one of them is preferred over the other, and the more intrinsic object doesn't live in the Grassmannian. It lives in this space, right? And it's the polygon itself. Okay? All right, but so that describes the inside. But in fact, we need a little bit more. Because if I just give you a bunch of z's, how do I know that they're ordered like this to look like a convex polygon? Okay? What does it take for them to be ordered? Well, let's go back. Let me remind you let me So this is a formula with a half in front for the area of a triangle that you probably learned at some point in your high school education, probably grade 4 if you're from Eastern Europe or something. Okay. Probably college if you're American. Okay, so there is that. So you've seen this formula for the area of a triangle in terms of a determinant. And of course, there's a more beautiful way of writing this formula. There's a more beautiful way of writing this formula projectively, because again, I've just fixed the top components. I've just fixed the top components to 1, so I can write it as, for example, ZA, ZB, ZC divided by some, or I guess I call them X here. So XA, XB, XC, and that's divided by some XA dot, something that plays the role of infinity, XB dot Y, XC dot Y, okay? But anyway, XA, XB, XC, and of course we already said, when this vanishes, it has the interpretation of the points being collinear. But all I want to point out is that it has a sign, and so the sign tells you how the triangle is oriented, okay? Whether it's oriented one way or the other. So, in order for this polygon to be convex, every ordered triangle has got to be oriented the same way. So 1, 3, 4, 1, 3, 5, 1, 4, 6. Every triangle has to go around in the same orientation. Okay? So in order for the triangle to be convex, it's also important that all the minors of the z's, all these 3 by 3 determinants, ZA, ZB, ZC, they should all be positive when A is less than B is less than C. Okay? That's what guarantees that the polygon is convex. Okay? So you see that even something as simple and dumb as a convex polygon is slightly sophisticated. Right? So let's write the formula again with feeling. So it's y equals CA summed over A, so the particle index or the vertex index, ZAI, where these are fixed external data, but which are positive in the sense that ZA, ZB, ZC, they're positive in the sense of the positive Grassmannian. That the ordered minors made out of the z's, if I may think of the z's as the 3 by n matrix, the ordered minors in terms of the z's are all positive, but they're fixed, and your scan over CA, C in the positive G1n. Okay? And in this way, we end up with a y that lives inside G13. Okay? Nothing other than P2. So lines in 3 dimensions. Okay? This just means that there's one y, and this index I is running from 1 to 3, since I'm doing everything projectively here. Okay, so that's the definition of the inside of a polygon. You see, it's the jamming together of 2 separate positivities. We have positive external data and a positive sum over the positive external data, where the positive sum is in the sense of the positive data is in the sense of the positive Grassmannian, and so is the positive sum here, although here, since there's only one y, this doesn't look fancy yet. We don't see any minors. This is just saying that the components of the c's are individually positive. Okay? But now, with that definition, now let's try to explain to a blind person why that sum of 1 II plus 1 covers the polygon and so on, right? We want to explain. For example, from the picture, it's immediately obvious. What are the boundaries of the polygon? What are the lines that are the boundaries of the polygon? The line 1, 2, 2, 3, 3, 4, and so on, right? But that's just because we can draw it and we're used to it. If I just give you this formula, where does it say 1, 2, 2, 3, 3? There doesn't seem to be anything there, right? I just have these. I have some ordering, but why do consecutive things? Where does I plus 1 come from? Where does all of that stuff come from? Okay, how can we see that without drawing the picture? So let's just do that, and once we see how to do that there, we will, what?
Maybe we can take a...
Oh, we want to take a break?
Just go until dinner.
Oh, you want to take a little, is this?
The dinner will be at 6.
Yeah, okay, that's fine. We have 45 minutes, so, but you want to take a little break? Is that what you're suggesting?
I don't know, if to take break now, or otherwise we don't have to take break.
Break, yes? Okay, he says break, yes. So I just don't want to see you slipping him a 20, though, you know. So, okay, why don't we take a little break? This is a good time to take a break. Yeah. Yes.